Okay, this video is the overview for section 4.3, optimization. And if you're American, you put a Z in for the S. Go figure. Okay, this video will be here. Hey, you're almost guaranteed to get a merit or an excellence level optimization question in the external exam, sometimes both. Okay, so to prove that to you, if we jumped down to module 4 review here and clicked on this one here, old exam questions, and not quite sure what's over there. So 2013 there was an E, there were 2 excellence questions. In fact, there was 3 and a merit. That's overkill. 2014 was an E, an M, and an E. 2015 was 2 excellence questions. 2016 was 2 excellences and a merit question. 17 merit, excellence. 18 merit, excellence. 2019 just a merit. Okay, so I've stopped there, but is the trend going to continue? As you've just hopefully seen right there, this, if you're targeting a top grade in the 6 credit differentiation external paper, then really have a go at targeting optimization problems, okay? And it's a real key essential part of differentiation paper. It's a really key application of it. So how to do this? Now you would in theory had some exposure to this in your year 12 understanding. Okay, so here's the plan. Watch this here, really good graphics, good colors. And I'm going to say it's pitched at level 2, which is last year, which is good intro. This here is literally Tahi Maths level 2 algebra paper. Sorry, level 2 calculus paper and his optimization one there. If you were to look in that, actually this document there is, I've actually grabbed it from here. And basically what you're seeing here is 8 steps to follow. Okay, now that's 8's a bit overkill really, but yeah. And on the right here is DELS-DEBT, which is, that's copied from New Lake. Their acronym, if you can think, DELDIPS or something or other. Hey, the key thing is you can't just jump to the answer. You've got to follow some logical steps. And yes, the algebra is going to get a bit fiddly, especially for me in step 4 here, or step L and S. In fact, before you differentiate, it's a differentiation paper, you've got to actually build your problem. You've actually got to come up with your expression, that's the hard bit. And sometimes you'll see there's 2 variables and you've got to fiddle with it to get one variable differentiate in terms of one variable, x or time or whatever, okay? So going back to here, that's why that's in front of you here. Use the 8 steps below left, or New Lake's DELS, DEB, DEBIT acronym shown on the right here. Okay, so definitely I'll be doing some entry-level, merit-level stuff, which would have been merit excellence from last year, and then building. And the key to it is your algebra and how you set up the problem. 4 pages there, no, 3 pages. Definitely read New Lake. Look at this. Let's have a quick look at this one here. Okay. So yeah, these are the things you could hit. Now, sometimes is it a maximum or is it a minima? Okay, but either one is optimizing, right? Maxima, minima. Could be area, volume, money, surface area of objects, waste, staffing, heck, time. Okay, so the math stuff and the actual real life web applications in biology, optimizing herd herd numbers in a particular area with prey and predators relating to each other, etc. Okay, so that looks classic year 13. You've got a pretty interesting, scary looking, that looks product rule to me. Okay, you've got an expression, but that thing's already given to you. This is why it's actually an easy example. And you just have to, that's what it looks like. And obviously there's clearly a maxima point there, and it's happening around there somewhere. And you have to work out the temperature and I guess when it's happening. There you go. Time equals 2. Hey, if you get a negative value for time, you can't go back in time that I'm aware of. Okay. Yeah, this is cool. There's the other part of the relationship. We're only interested at time equals 0 onwards. So this part of the curve, ignore it. Okay, this one, your classic Coke aluminium can. Can you design the radius of it such that minimum surface, as in the less amount of volume of aluminium? So for the same amount of liquid capacity, can you reduce the amount of tin capacity? And hey, save money. Good concept. So that one there is obviously a volume surface area thing, minimum, okay? And you have to start to flesh out, it's a net, okay? What are the areas, etc., etc. And here you'll find the issue. You've got two variables, R and H, and you have to make the call, which one are you going to optimize to get that result there. Okay, so as you work your way through here, team, it's algebra heavy, and looks like we're using graphing calculator here. Enjoy it. Okay, so again, fantastic, Mr. Infinity Plus One here, Mr. Chanda, really good stuff. Optimization from STEM. There it is, the whole module on it. Look at their examples, and after a while, if you do, 5 problems, you're probably confident to get a merit one, but you've got to do more than that to really be in the space. In an assessment event in front of you, this is what I need to do. This is a demanding level 3 calculus paper, and it just comes down to, are you going to put the time and energy in and get the help and support where you get stuck at home? And that's why Mr. Chanda here, STEM Online, really good. Okay, to help you, I do not have New Lake here. Okay, instead, over the last couple of years, my students, I've produced these 2 PowerPoints. So I'm just going to quickly go through them with you. This PowerPoint starts off pretty simple. Okay, in fact, let's just do this one right now. Okay, 2 numbers have a sum. Hello, I'm just seeing some extra people join us at the top up there. Fascinating. Who are you? Okay. Ibex and Squirrel and Dingo. Okay, so what I want you to do is excuse me, click on this, click on you. Okay, so 2 numbers have a sum of 11. What is the maximum value of their product? So 2 numbers, good old x plus y equal 11. It said the sum of them. What is the maximum value of their product? So we could say P for product equals XY. And so we've got an expression we want to optimize. Now you can't go dp by dx because you've got 2 variables. So obviously you have to take this bit here. Let's eliminate the y. So y is equal to 11 minus x. So your p expression is x times this thing. Now I could do product rule here, but no, I'm going to go 11x minus x squared. dp by dx is 11 minus 2x. Okay, so we've got the first order derivative, put it equal to 0. And what happens here? We're getting 2x equal to 11, x equals 5.5. So the optimum will occur, and this is going to be the maximum. If you were to graph this, if you solve that, one solution here, This is product, and at 5.5, so basically what we discovered here, hey look, if x equals that, y is also going to be what? 5.5, so it's a square, by the way. That times that, 5.5 squared is going to be your maximum product. And I can't be bothered. Yes. Put it on the calculator. 5.5 squared. The answer was 30.25. You know, if you had gone for 4, when x is 4, then y would have been 7. 4 times 7 is 28. So, no, it's getting close to it. If we went for 5, you're going to get what? 5 and 6. So 5 times 6 is 30, but still slightly less than 30.25. Okay, so that was an example of literally what I just did there, believe it or not, was I probably did read the question twice. Didn't highlight anything. Did I draw a diagram after the event? Yep. Okay. Did I write the function in terms of one variable? Yes. I eventually got a value for p for product equals x bracket 11 minus x. So I definitely did that one. And then did I differentiate? Yes. And then did I put it equal to 0 and solve for x? Did I check to see it was a maxima? Oops. Okay, let's just do that now. So there's the first derivative. There, sorry. The second derivative, p double dash, d double dash p dx squared. That's going to be negative. So straight away, what it means is there's only one option, and that value at x equals 5 is going to be a maxima, because the second derivative is by default negative. And graphically, I could have got the same answer as well. Okay, that was rushed, but hopefully you get the idea. And did we check it? Yeah, I thought we did. You know, we put a graph here and we looked at bits either side of it, and you know, it was confirmation that 5.5 is the correct answer. The two numbers are 5.5. Were you expecting decimals? I think, yeah, that's okay. Righty, so this one here is a classic. If you've got 20 meters of fencing, for example, 4.8, 5.2, that's the perimeter. And if you basically go to this app here and you can graphically see the answer, and you can obviously predict, you can see where the maximum is going to happen. Can you algebraically show the same thing? That's we challenge. Variations on this perimeter one. This is American. You've got a barn fence or something, and you've got 40 feet. It's American. So you don't obviously need that section of fence. You just need X and X. So you're developing the problem. The length is 20, and you've got, what's that? No, length is 40, sorry. Yeah, X plus X and 40 minus 2X, that is equal to, slow down. Okay, that the perimeter is going to be 40, and so there's your expression. Perimeter, or L, length, equals, no, length is this length thing here. Yep. Okay. Yep. So length would be the total minus 2x. And now you have the two sides of it because you're after area. So length times width. So that times that gives you the expression for area. Expand, differentiate, put equal to 0, and test it. Okay. This is good. If you were to play the slideshow, this is a classic merit level. It's an easy merit optimizing problem. So I'm not going to spoil it. I want you to have a look at it and go look at the answers there afterwards. This one we'll probably do in class, VC session that is. What happens if you've got circle ends? The circumference here is 400, and you want to optimize the maximum area inside that running track. Okay. Your classic box problem. This is an example from page 155. If you want to see it graphically on GeoGebra, there's a link there, or there's another link there. And back to 2017, good problem here. And the cool thing is we have Mr. Chanda here to explain it to you. Okay, and 2018, Mr. Chanda here explaining it to you. Some classic, this is solid year 13 merit stuff, looking at this one here. And then we've got some New Lake stuff. 338, my messy handwriting, but this is from previous years, so I might update this at some stage. But anyway, you should be able to follow that. And we've got some New Lake ones. So what you're seeing here is you possibly might say, I'm sick of New Lake, just do the NCA questions in this. Good practice. Okay, going back to here, and this is the money question. If you're after the excellence overall, you are going to get an opportunity to get an excellence, most likely with an optimization problem question. Okay, so same process. What I've got here basically is NCA questions. That's the best standard. Just go for those. So 2014, I'm thinking that's quite doable. This one here, and I've got a GeoGebra app which sort of models it. This one's tricky. Savior, that's actually a New Lake one. If you can do that, you're looking very good. This one's subtle. Put something inside a cone. What's the optimum size, etc. And here he is explaining it. And here's a wee clue, ratios. This one's interesting. And again, he explains it. Fantastic. And to finish off with here, a classic, putting a cylinder inside a sphere. For one of them being fixed, what's the maximum volume of the cylinder inside? What's all the constraints? How are you going to set up your problem? Away you go. So guys, you're really doing a lot of algebra if you're getting up to this stage here. Right, to finish off with, that is it. Yep. Don't forget, these ones here had a selection of problems, but if you want lots of problems, obviously click on here, and there would be some of these are featured. This one here wasn't, for example, Grasmere and Upper Blenheim area. That one, that's another one which I haven't, there's lots of extra problems here for you to look at. And don't forget, 2017, I believe, 2018, Mr. Chanda. Yeah, this one here, the goalpost one, a bit of trig optimization. That one's tricky. There's lots of practice here for you. So here's what I'm saying is basically you can probably ignore New Lake and go to the real deal. Go to the NZQA standard questions. That just a bit of humour at the end here. We've seen optimizing. Looks like we get up to advanced calculus in terms of math skill as we progress with time. Where are we at the moment? Here somewhere. Okay, and after that, you're basically stuck to spreadsheets and in your post-engineering university career or whatever you're doing. Enjoy.